Imagine a line at a candy shop. If you let the child with the smallest bag of candy finish first, the line clears faster, because many little bags disappear quickly. Shortest job first (SJF) works the same way for computer programs. It runs the program that needs the least amount of CPU time its burst before the others. The main idea is to minimize the total waiting time of all programs, just like getting the most people out of the line fastest makes everyone happier. This is why SJF is often called the most efficient scheduling rule, when we only care about average waiting time. Formal definition: non-preemptive. There is a set of processes P equals set of P sub 1, P sub 2, up to P sub n. Each process P sub I arrives at time a sub I and has a known CPU burst length B sub I. The scheduler can only make a decision when the CPU becomes idle, that is, after a process finishes. At that moment, it selects the ready process with the smallest B sub I among all processes, with a sub I less than or equal to current time. Assumptions: 1. All burst times are known exactly at arrival or can be predicted perfectly. 2. No new process can interrupt a running one. Once a process starts, it runs to completion, hence non-preemptive. 3. Context switch overhead is ignored for the theoretical model. This definition guarantees that the schedule produced minimizes the sum of waiting times under those assumptions. Formal definition: preemptive SJF, also called shortest remaining time first SRTF colon. Same set P with arrival times a sub I and initial burst lengths B sub I period. At any moment, the scheduler looks at the remaining CPU time R sub I of T, for each ready process the part of B sub I that has not yet been executed period. Whenever a new process arrives or a running process finishes a time slice, the scheduler may interrupt the currently running process if another ready process has a smaller remaining time. The selected process is the one with the minimum of R sub I of T. Assumptions: 1. Remaining times are known or perfectly predicted. 2. Preemption is allowed with negligible cost. 3. The system can switch instantly, so the schedule can change at any arrival instant. This policy also yields the minimum possible sum of waiting times, but now the schedule can change many times during a process's life. Explanation: let us work with 3 processes that all arrive at time 0. Process P1 has a burst time of 8 milliseconds, process P2 has a burst time of 4 milliseconds, process P3 has a burst time of 2 milliseconds. Non-preemptive short job first. Order is P3 to P2 to P1. Completion times: C3 equals 2, C2 equals 2 plus 4 equals 6, C1 equals 6 plus 8 equals 14. Waiting times: W3 equals start minus arrival equals 0 minus 0 equals 0. W2 equals 2 minus 0 equals 2, W1 equals 6 minus 0 equals 6. Turnaround times: T3 equals C3 minus A3 equals 2, T2 equals 6, T1 equals 14. Average waiting equals open parenthesis 0 plus 2 plus 6 close parenthesis, divided by 3 equals 8/3, approximately 2.67 milliseconds. Average turnaround equals open parenthesis 2 plus 6 plus 14 close parenthesis, divided by 3 equals 22/3, approximately 7.33 milliseconds. Preemptive short job first, shortest remaining time first. Suppose a new process P4 arrives at time 1 with burst 1. The schedule becomes: process P3 runs from 0 to 2, then at time 1 process P4 arrives with remaining time 1 less than the remaining time of P3, the CPU switches to P4, finishes at 2, then returns to P3, and so on. By recomputing start and finish times, you can see that the averages are still the theoretical minimum, but the math follows the same formulas. W sub I equals S sub I minus A sub I, where S sub I is the first time the process gets CPU, and T sub I equals C sub I minus A sub I. The sum of all W sub I is minimized by shortest remaining time first. Starvation happens when a long-running process keeps getting pushed aside because new short jobs keep arriving. Imagine a child with a huge bag of candy that never gets to the checkout because many kids with tiny bags keep coming. The child may wait forever, that is starvation. In SJF, we can avoid it by using aging. Gradually increase the priority or effectively the perceived burst length of waiting processes. For example, every time unit awaiting process's estimated burst could be reduced by a small factor, making it look shorter over time, so eventually it will be chosen. Another simple technique is to set a maximum wait time. If a process has waited longer than that, the scheduler forces it to run regardless of its length. These tricks keep the system fair while still enjoying SJF's low average waiting time. Average waiting time smallest optimal can be large if long jobs arrive early depends on priority values, low priority jobs may starve moderate depends on quantum size. Fairness poor for long jobs starvation very fair order of arrival depends on priority assignment may starve low priority fair if quantum is reasonable. Overhead low just sort once very low simple queue may need priority tables reordering higher context switch each quantum. Responsiveness good for short jobs bad for interactive long jobs bad. For interactive, if long job at front good for high priority interactive tasks, good for interactive short quantum. FCFS is like standing in line exactly in the order you entered simple, but can make the line move slowly if someone has a huge stack of books. Priority scheduling is like letting VIPs cut in line they get served quickly, but others may wait a long time. Round robin gives everyone a tiny turn like letting each child take a single candy. Then going back to the start ensures nobody waits forever, but many switches happen. SJF tries to keep the line moving fastest overall by always serving the smallest stack first, which gives the best average wait, but can be unfair to the big stacks. The OS keeps a ready queue that contains all processes that are ready to use the CPU for SJF. We need the queue ordered by the estimated CPU burst or remaining time for the preemptive version. Data structure a min heap or a balanced binary search tree works well because it gives O of log n insertion when a new process arrives, and O of 1 to peek at the smallest element. Selection algorithm non-preemptive when the CPU becomes idle, remove the root of the heap. This is the process with the smallest burst. The process runs to completion, then the next smallest is taken. Selection algorithm preemptive SRTF, every time a new process arrives insert it into the heap with its remaining time as the key. Compare the new key with the remaining time of the currently running process. If the new key is smaller issue a context switch push the current process back into the heap with its updated remaining time and pop the new shortest one to run. Because the heap always gives the minimum the scheduler never has to scan the whole list. What to store process ID total burst remaining time arrival time and optionally the last time it was scheduled for aging calculations. This organization makes the SJF decision fast enough for a real operating system. In a real system, we rarely know the exact CPU burst before a process runs. The OS therefore estimates it, often using exponential averaging. Tau sub n plus 1 equals alpha times t sub n plus 1 minus alpha times tau sub n. T sub n is the actual length of the nth observed CPU burst. Tau sub n is the previous estimate. Alpha 0 less than or equal to alpha less than or equal to 1 controls how quickly the estimate reacts to recent behavior. If alpha is close to 1, the estimate follows the latest burst closely. If it is near 0, the estimate changes slowly. The OS updates tau after each CPU burst and uses the newest tau as the predicted next burst length for SJF ordering. Impact on performance. Good estimates make SJF close to optimal, giving low average waiting time. Bad estimates, for example always guessing a very short burst, can cause the scheduler to pick a process that actually takes long, hurting performance and increasing context switch overhead in the preemptive case. The choice of alpha is a trade-off. A high value reacts fast to changes in program behavior but may be noisy. A low value smooths out variations but may be stale for programs that change phases. Thus, accurate burst time estimation is the practical key that determines whether SJF works well in a live system.